My name is Hibiki Yamamoto. I am a first-year master student at Ritsumeikan University and belongs to Molecular Pharmaceutics Lab. My presentation title is Intestinal Precipitation of Weak-based drugs simulated by Population Balance Model. Prediction of oral absorption is important in drug discovery and development. Recently, approaches using physiologically based biopharmaceutics modeling (PBBM) have been investigated to predict the oral absorption. PBBM is mechanism-based approach. However, it is difficult to predict the precipitation process in the gastrointestinal tract. To predict the precipitation process, in vitro, in silico, in vivo prediction, IVIS-IV approaches have been investigated. IVIS-IV is empirical kinetic model. In IVIS-IV, precipitation process coefficients are back estimated from the in vitro precipitation data. Conventionally, a first-order type kinetic model have been used to represent the precipitation profile. However, it might not capture the characteristics of precipitation profile such as the induction time. Induction time here is the time drug crystal precipitate. The first-order type kinetic model might not represent the induction time. To predict the precipitation profile in the gastrointestinal tract, we need a mathematical model. In chemical engineering, population balance model has been successfully applied to predict the crystallization process. In this study, we aim to the population balance model accurately simulates the precipitation profile. To begin with, I will explain the population balance model. When drugs are dissolved in water, drug molecules gather and form crystal nuclei. The primary nucleation occurs the solution-only states, and secondary nucleation occurs from the states where crystal already exists. Together, these two are called nucleation. Then, the nuclei grow into the crystal. In population balance model, it is possible to consider primary nucleation, secondary nucleation, and crystal growth separately. The formula for primary nucleation rate is K1 times the degree of supersaturation to the power of B1. Secondary nucleation rate is K2 times the degree of supersaturation to the power of B2 times the third moment. Crystal growth rate is Kg times the degree of supersaturation to the power of G. 6 of K1, B1, K2, B2, Kg, and Z are experimental coefficients. The formula for calculating the drug concentration is shown. Drug concentration differentiated by time equal -3 times the crystal growth rate, drug density, volume shape factor, and second moment. I'll explain the method. We used dipyridamole, haloperidol, papaverine, phenatopyridine, and tosafloxacin as model drugs. Table 1 shows the PK and an equilibrium solubility of model drugs at pH 6.5 and 37 degrees Celsius. Low solubility basic drugs with a pK range of 5.2 to 8.7 and an equilibrium solubility range of 2 to 102 microgram per ml were selected. I'll explain the outline of the experiment. First, conduction of the pH shift test. Second, construction of population balance model. Third, prediction of the result in the artificial stomach intestine transfer ASIT test. Finally, comparison of the predicted profile and measured profile in the ASIT test. I will explain detail on the next slide. The pH shift test was conducted to measure the precipitation profile. Each drug was dissolved in pH 3.0 HCl. 287 millimolar phosphate buffer was added to the drug solution and then shifted to pH 6.5. Precipitation profile were measured. Precipitated particles were observed using a polarized light microscope, and the particle sizes were measured using an image J. Each coefficient of population balance model was determined by the pH shift test data. The precipitation profile in the ASIT test was predicted by the constructed model. ASIT test is in vivo surrogate. We conducted the ASIT test. Drug solution infused to the phosphate buffer at 3 ml per minute. Finally, the precipitation profile in the ASIT test was compared with the predicted profile. In this slide, I will explain the determination of coefficient. When 6 coefficients were determined to fit the pH shift test data, coefficient cannot be determined. Therefore, the number of coefficients should be reduced. First, I will explain the coefficient of primary nucleation K1 and B1. They are calculated using this formula from the induction time and degree of supersaturation. The number density was set to 1000 for all drugs. Figure 1 shows the relationship between the degree of supersaturation and induction time. The x-axis indicates the degree of supersaturation, and the y-axis indicates the induction time. Coefficient of B1 was calculated from the slope, and the K1 was calculated from the intercept. Next, I will explain the coefficient of secondary nucleation K2 and B2. The secondary nucleation is sensitive to the paddle rotation speed because crystal collision induced the secondary nucleation. Therefore, we investigate the effect of the paddle rotation speed on the precipitation profile. Figure 2 shows the precipitation profile in the pH shift test of dipyridamole. The x-axis indicates the time, and the y-axis indicates the concentration. The paddle rotation speed shows no effect on precipitation profile. From this result, the effect of the paddle rotation speed has little impact on secondary nucleation. Therefore, the secondary nucleation was neglected by setting K2 and B2 to be 0 for all drugs. Finally, I will explain the coefficient of crystal growth rate, Kg and Z. It is known that the G is the range of 1 to 2, so G was set to 2 for all drugs. Finally, Kg was determined by visually fitting to the pH shift test data. I will explain the result when using dipyridamole. Figure 3 shows the precipitation profile in the pH shift test. The x-axis indicates the time, and the y-axis indicates the concentration. Figure 4 shows the relationship between the degree of supersaturation and the induction time. The x-axis indicates the degree of supersaturation, and the y-axis indicates the induction time. Coefficient of K1 and B1 were calculated using this result. Figure 5 shows the precipitation profile in the pH shift test and fitting curve. The x-axis indicates the time, and the y-axis indicates the concentration. Dots indicates the measured value, and the straight lines indicates the fitting curve of population balance model. Coefficient of Kg was determined from this result. Each coefficient was used to predict the result of the ASIT test. Figure 6 shows the precipitation profile in the ASIT test and predicted curve. The x-axis indicates the time, and the y-axis indicates the concentration, and straight lines indicates the predicted curve of population balance model. The measured value are shown. Both of Cmax and Tmax were predicted within about a 1.5-fold error. Table 2 shows the particle sizes in the ASIT test. The particle sizes were predicted within about a 2-fold error. Same experiments were conducted with other drugs. Figure 7 shows the relationship between the degree of supersaturation and induction time. Figure 8 shows the precipitation profile in the pH shift test and fitting curve. Table 3 shows the coefficient of population balance model. Each coefficient was used to predict the result of the ASIT test. Figure 9 shows the precipitation profile in the ASIT test and predicted curve. Both of Cmax and Tmax were predicted within about a 1.5-fold error for haloperidol, phenatopyridine, and tosafloxacin, within about a 2-fold error for papaverine. Table 4 shows the coefficient of population balance model. Coefficient for K1 was ranged of 8.3 times the 10 to the power minus 4 to 1.4. B1 ranged of 2.0 to 4.2. Kz ranged of 2.8 times the 10 to the power minus 9 to 9.0 times the 10 to the power minus 7. Table 5 shows the particle sizes in the ASIT test. Particle sizes was predicted within about a 2-fold error for dipyridamole and papaverine, 1.5-fold error for haloperidol, 1.2-fold error for phenatopyridine, and 3-fold error for tosafloxacin. Let's move on to the discussion. The number of coefficients was reduced to allow coefficient identification by the pH shift test data. Population balance model appropriately predicted the precipitation profile and the particle sizes in the ASIT test. In conclusion, population balance model can be used to predict the precipitation profile of basic drugs in the gastrointestinal tract. Thank you for listening.